Welcome to that seminar. Today we are opening this season of that seminar this academic year with talk by Mathias Drton. So I'll first give you a little bit of an intro about Mathias. So I think probably many of you know this. So Mathias on methods and theory in the field of statistics. His main interest is the analysis of complex multivariate data, and the main focus lies on graphical models which capture fine causal relationships. The aim of the research is, among others, and probability theory, under which circumstances data allows conclusions about causal relationships and to develop efficient methods for their estimation. A little bit about the history. After studying in Oxford, Mathias received his doctorate in statistics in 2004 from the University of Washington, Seattle. He then worked as a postdoctoral fellow at UC Berkeley. Then from 2005 to 2012, he was an assistant associate and then full professor at the University of Chicago. In 2012, he became professor of statistics at the University of Washington. He spent the year 2018-2019 at the University of Copenhagen. And lastly, since 2019, Mathias is a professor of mathematical statistics at Welcome, Mathias.
Yeah. Come in. No. Yeah, thanks for having me. I feel like I invited myself a little bit, but oh no, okay.
One thing, during the talk, please raise your hand and we'll call on you to answer. If you're on Zoom, you can write your question in the chat or raise your hand and I'll call you. All right, sorry.
Yeah, thanks, Emma. So this was the bio that every professor at TUM has to give a bio to the central administration, so everybody gets a page. That also, the only thing she left out, I think, is my birth date, which in Germany they put on the website. But anyway, so thanks for having me. So I'm gonna tell you about so the line of work we're doing on what we're calling graphical continuous Lyapunov models. And so far, the stuff that is out are two papers with one of the students in Munich, Philipp Dettling, and then different collaborators. And so this first one will come out in one of the SciAm journals, Matrix Analysis, which is also with Niels Hansen from Copenhagen, whom you might know. And then the other one is with Mladen Koller, but that's still just a preprint on arXiv. And so okay, now this does not work. Okay, maybe I'm probably not in it. Okay, all right, so motivation is, so from a grand scheme kind of perspective, causal discovery. So looking at dependent structure in multivariate data and trying to infer back something about the causal relationships that might be there and that have led to the dependencies that you see in the data. And if you want to play this game, then you need models. So you need to somehow model how a regulatory network of some kind leads to stochastic dependencies in multivariate observations. And so this is this continually overused example from this paper by Sachs et al. On some protein signaling network. But so this is the game. And so then the question is, what kind of models do people use to model the effects of causal relationships and how that leads to a joint distribution for multivariate observations. And so the common approach that is most widely adopted is this paradigm of either directed graphical models or structural equation models, or if you emphasize the causal interpretation, structural causal models, in which you model by thinking about some, so you model an association, right, that encodes what you think about how variables play together. And then the actual model is obtained by postulating that each variable in the system, which corresponds to one of the nodes of the graph, is a noisy function of other variables in the system. So when we draw a picture like this one here, where there's some, so this is an instrumental kind of scenario where you maybe study smoking behavior, how it impacts health, then there may be genetics involved, and maybe you think about a tax rate because you want to win a Nobel Prize in econ. And then, so you would say things like, okay, looking at this picture, what this graph says is that x2, this variable, should functionally depend on x1 and x4. So you're going to write down equations of this type. X2 is a sum function of x1 and x4, and then always noise specific to this functional relationship. And you do this for every variable in turn. And to inject stochasticity, you're looking at these noise random variables, and we're going to say they are independent random variables, and each one of them has some distribution, which distribution is a parameter of the model. And then you commit to something about what kind of functions you're interested in. These are also parameters of the model. Once you've written down this equation system, you can solve for how the x's are functions of the epsilons. And this gives you a push forward from the joint distribution, this product distribution, that's the joint distribution of these errors epsilon, to the joint distribution of the x's. And this is your model. And it's parameterized in terms of these functions and the distributions of the noise. Oftentimes, if you look at large scale models, it's interesting to just go with a simple scenario, a seemingly simple scenario of saying, say, everything linear, for instance, right? So then you would have a graphical model in which these coefficients in the linear equations there are the unknown parameters, and they are then the primary things of interest. Okay, so this is a very commonly used setup. And this is also something that we understand incredibly well, provided that the picture you started with is what people call a DAG, so a acyclic digraph, or a directed graph that does not contain any directed cycles. If you're looking at models that are associated to such DAGs, then we know a lot about them, right? We understand exactly what they say in terms of, let's say, conditional independence relations among the variables. We know how to deal with them. Estimation is comparatively easy, maybe by regression techniques. And we have lots and lots of tools to do things like learn DAGs empirically through different algorithms and justified by things that Thomas did and Chris Meek did and so on. So there's a super solid theory also about what can you learn and what can you not learn in terms of model equivalence. So when do different graphs give you the same statistical model and so on. So this is super well understood, I would say, and this is sort of the hallmark of graphical models theory. But for many systems, you can also think about, okay, well, really, is this reasonable to think about that the system is described by a DAG that is free of feedback loops effectively? So it's free of directed cycles. And maybe in many cases, you would say, well, this organism is alive because it has some way of regulating itself. So maybe there should be some feedback loops. And what have people also been doing for a long time is to just stay with this paradigm. I mean, you can write down equations as you want. Also, this graph is directed cycles. And if you do it in a linear realm, then it's relatively easy to understand even when there are cycles, when such an equation system has a unique solution in the x's. So over a DAG, it's just a triangular system, so it trivially has a unique solution. But if it has feedback cycles, it's not immediately clear. If it was nonlinear, this would be complicated to think. Linear case is still relatively easy to check in on a determinant to say that there's a unique function. But so you can do this, just include directed cycles here and run with it. But I would say this is far more complicated. Right? So you have to have somebody at least as smart as Thomas and Chris and so on to get some theory going like this. And it's far more complicated to understand how these models behave. It's far more complicated to do statistics about them. But it's also a bit, it's not as obvious as one might feel to say, what does it really mean when I start to include feedback loops and I solve these equations? Why am I interested in the dependent structure that comes out of that? Okay, so in order to justify this, there's a series of papers around, starting with a classic paper by an economist, Fisher. Thomas is going to correct me if I say something wrong, right? But Franklin Fisher, so he wrote about how you can justify these models as some equilibrium situation where you talk about some system evolving over time, and then there's some funny conditions about the noise being always the same at different times. And you think about the measurement being a accumulation of everything that has happened over time, and then you can justify these kind of models. And then other people have written about connecting them to points of dynamical systems and so on. But so these attempts to interpret these models with directed cycles, in some way they try to post hoc tie this to temporal processes, right? So you're trying to say, what I get out of writing these equations as a dependent structure, it does have some meaning with respect to some process that may evolve over time in nature, and it is something that you can relate to an actual scientific phenomenon. So, but this is all a bit so post hoc. So what we did, well, what we want to do in this series of little projects we have going on is to not do that and just immediately start with this perspective that what you have measured is a one-time cross-sectional snapshot of some multivariate time series, some multivariate stochastic process that evolves over time. And so you get to see, let's say, some organism in biology living its life. And when you measure it, unfortunately, it's such that you kill it. So you measure it one time, there's no time series and nothing, you just measure it one time, and then you see some dependence in this cross-section. And then maybe you get another data point by growing another organism, letting it live, and so on, and measuring again. And so the goal now is to think about models that are derived from a temporal process. And so what we're going to do is we think about, so there's some temporal process, it runs, it reaches a steady state, so it's in some form of equilibrium, and then we measure one time. And then we do it again, and we get an IID sample, and the dependent structure is derived from this temporal process. Okay, so then, what kind of temporal process do you want to look at? So now lots of choices. So this is what we're going to do. So we're going to think about what is, in a way, the canonical continuous time version of an autoregressive process of order 1. And so this is multivariate Ornstein-Uhlenbeck process. So the setup is, so this is also based on what Niels Hansen did with his postdoc Gerardo Varando in a 2020 UAI paper. And for reasons that are unclear to me, by a postdoc at TUM Operating Research in a single author paper that's just sitting around the archive. But so she also did this. I don't know why, but she's not in academics anymore. But so what we're then saying is, so our observations are an IID sample of p vectors. And the distribution of each one of these p vectors is the equilibrium distribution of a multivariate Ornstein-Uhlenbeck process. So this process you can define through some stochastic differential equation, where there's some drift matrix specifying how the time evolution goes across the coordinates of this vector xt, where t is the time index. And so this will be a stable matrix with eigenvalues, negative real part. And it reverts back to some mean vector mu. That's a parameter of the process. This matrix is a parameter of the process. And then in this time evolution, there is a Wiener process Brownian motion that injects noise. And there is a matrix D that scales this noise process. Okay. All right. So whatever it is, this is some continuous time process. And there are three parameters, this vector mu, and this drift matrix M, and this matrix D that scales this noise process W. The main thing of interest is this matrix M. This matrix M reveals how across time, different coordinates of this vector xt influence each other. So this is how in this system that evolves over time, how different variables in this vector drive each other. Okay, so this is the object of interest. So let's call this a drift matrix. And so this is the setup. Okay, so you get observations. It's each observation you get is this one such process has lived its life, and then we measure once, and then there's another independent one that lives its life, and we get to see it once. This is a continuous time setup, and so I'm going to all talk about that. You could also do a discrete time setup. That's actually what Adrian and his student Chad Young and another UW person that I don't know personally have done in a 2019 paper. They looked at some questions surrounding a discrete time version of this, where you don't say it's a continuous time process, but some discrete time vector autoregressive process of order. Yep.
I'm just confused because it says X1 through Xn in RP.
Yeah.
So where's time there?
So there's no time here. So you get a data matrix that say has n rows. Each row holds a p varied observation. It's coming from one process this is a p-dimensional process evolved over time. So this describes the process that at some time point t far along, when the distribution of the process has reached a steady state, so there's just one distribution that's associated to these parameters, and that tells you what the distribution is of the vector in one row. And then you see it IID again and again. Okay? Yeah, exactly. At the IID sample, and each point in the sample is you see this temporal process once. So if you were smart enough and had the ability to observe the whole time series, then life would be much easier and you could do much more things. But we're assuming that we don't have the experimental technology, or we just didn't measure anything but one time bar. Okay, so then all good and fine. But so what does this actually do concretely? So what am I talking about? So M is a stable matrix. I already said that, right? So eigenvalues with negative real part. And so if that matrix is stable, then this SDE gives you this process. And the steady state equilibrium distribution is a normal distribution. And so I need to tell you what is the mean vector and what is the covariance matrix. The mean vector is simply that thing mu that this reverts back to. And what the covariance matrix is then depends on this M and this D. And specifically, the covariance matrix sigma of this equilibrium distribution is a positive definite matrix sigma that solves this boxed in equation here, where you take this drift matrix M, which is a not necessarily symmetric P by P matrix, and then times sigma, which is now this covariance matrix I want to determine, plus sigma then the transpose of M. So this is a symmetric matrix, this sum. And it has to be equal to minus C, where C is D transpose. So the C is some sort of volatility matrix, you might want to call it. And so the covariance matrix is obtained by solving this equation. Okay, and so if this matrix equation has a unique solution in sigma, and that sigma is positive definite, that is a standard result about this equation, which is known as the Lyapunov equation, or to be very concrete, as the continuous Lyapunov equation, because it's derived from a continuous time process. And so this is why we call these continuous Lyapunov models. Okay, clear? So you don't need to know anything about stochastic differential equations or anything like that. You need to know the multivariate normal distribution and you need to know linear equations, okay? So this is how every choice of M and C leads to some sigma. So this is a parametrized covariance matrix as a function of M, okay? Now, if you think about this, you see that there's one indeterminacy immediately. So if I scale this equation, so I take M and I scale it with a scale gamma positive, and I scale it with gamma positive, then you preserve the solution sigma, right? Okay. So you cannot do anything about that. And so in some ways, that has something to do with, if I only give you a snapshot cross-sectionally one time, you cannot tell me how fast the process evolves, okay? There's nothing you can do about that. So we cannot ask questions that are perfectly about M and C. We can only ask questions up to a scaling, yeah? Okay. So then what we've done as a starting point is we assumed something simple, namely, that this matrix C is known up to a positive scalar, okay? Maybe, for instance, this is just isotropic noise that comes in. And so I'm going to just run with that now. And so if I assume C is known up to scalar, given that I cannot do anything about the scaling anyways, I might just study the problem with assuming that C is known, just have to keep in mind that I shouldn't be asking questions that are not scale invariant, okay? But for instance, I can ask a question about which entries in M are 0 or not. That's a question that is free of scaling, right? So this tolerates scaling. All right, so then going forward, I'm gonna say we're gonna be in a situation where the C is given, maybe it's the identity, or twice the identity for convenience. And M is the unknown parameter, and I wanna know something about M, which tells me how over time different variables in the system affect each other. Okay? So I'm then interested in models that say something about this matrix M in terms of sparsity. So maybe say this. So M is a P by P matrix that doesn't have to be symmetric. This equation is symmetric, okay? So the information content is, if this is a P by P system, you have P plus 1 choose 2 equations. And you're asking, if I revert back, if I say, what is the M that generated sigma, right? Then I'm asking a question, find me a P by P matrix on the basis of fewer equations than you have entries. So that's not possible. So the only thing interesting about learning about the system in terms of what is M on the basis of a covariance matrix is if you assume some low dimensional structure in it. So we're gonna look at, yeah.
So on our previous slide, I one other thing for me. So, okay, see we're assuming that it's with us to the top of the scale and then, like, if I knew M, then I could figure out sigma. If I knew sigma, I could figure it out. But I don't have.
No, unless you assume something about M is sparse or so.
Oh, I see.
Yeah.
Oh.
Mm-hmm.
Okay, good.
So if you give me sigma, so if you say I get a lot of data, I estimate the covariance matrix, what sort of matrices M gave rise to the sigma, there will always be a P choose 2-dimensional solution space. Mm-hmm. Yeah. So I'm interested in graphical models of this type, right? So I'm assuming my system is behaving according to some structured sparsity that is captured by a graph like this. And so if I look at a picture like this now, I'm not going to interpret it in terms of structural equations. I'm going to say it means that this matrix M is sparse. It has some diagonal entries that may be whatever they want to be, but then the off-diagonal entries can only be in the places where the edges are. And sometimes I do self loops to remind myself that I have these diagonal entries. Sometimes I don't. And so, and you forgive me. All right. So a graphical model is now you take a graph, not necessarily a DAG, and on looking at the edge set that says, I want to restrict M to be sparse according to where the edges are. And so I'm going to be interested in matrices M that live in this set that we sometimes call stab E, where it's of a graph, and it tells me where there may be non-zero entries in this matrix M. In addition, the stab says it has to be a stable matrix, so it defines a proper process that admits an equilibrium. Okay? Yeah? So graphical continuous Lyapunov models associated to graph G are just the covariance matrices that you get from these types of sparse matrices M when they're stable. Yep. Stable means it's a matrix that has eigenvalues with a negative real part. Okay. Right. So yeah. So that an assumption that yeah, so I don't know. I mean, graphical modeling, you sort of think about it in two ways often, right? So I can do it one way where I say I want to find statistical models associated to graphs. If I do it like that, I say, here's a graph we want to talk about. Associated to this graph is a parametrization, right? By assuming that M is sparse in this way, and then it creates a bunch of distributions associated to it. I think you're asking me about the backwards way. Is there a canonical graph associated to a given distribution? So that requires understanding equivalence of models and so on, right? Because it could, in principle, it's possible, and in general will be. If the graph is dense enough, there may be many different graphs that allow you to create the same covariance matrix sigma. And in that sense, it's not like undirected graphical modeling, right? You take a covariance matrix, you invert it, you look at its zero pattern, there's a graph. But this is not so clear here that there's a, yeah, but here it's not so clear, right? Yeah. And what exactly happens, I guess, is an open question. Okay. Yeah. Okay. So what have we looked at so far? So the first problem that we studied is parameter identifiability. So we said that you have this matrix equation. Its content are P plus 1 choose too many independent equations. And but you're after a P by P matrix. So then the question is, if you assume sparsity of a certain type for M, does that mean that given a covariance matrix, there's only one sparse matrix M that can give rise to this covariance matrix? Okay, that's identifiability. Yeah. So if you give me the covariance matrix, so the first question is M matrix, and we talked about it, right? No. Oh, the sparsity pattern of the matrix as given by some graph is then unique. That's the first question. And then the other question we looked at is how would you estimate this matrix M in practice? So if I give you, for instance, data, you estimate the covariance matrix, maybe on a sample covariance matrix sigma hat. How would you estimate M? And so one thing I thought that was exciting about this setup here is that you can write down an obvious convex program to do that by just looking at how well do you satisfy the Lyapunov equation in squared Frobenius norms as a quadratic function. And then you do what we've been doing, I don't know, in the last 20 years, and you tack on an L1 penalty. And this would give you a nice convex program that has the potential of allowing you to learn the sparsity structure in M in a tractable way. Okay, and so this is the second problem we looked at. Well, let me talk about identifiability first. Okay, so if you think about yeah. Sorry. So if you're in a situation where you're looking at a sparsity pattern where you don't have this injectivity, I mean, you could still work with these models, but then you're in a situation where you may be able from data, right? In statistics, if you get data, you can estimate the data generating distribution, right? This is all you can get out of my setup with IID sampling. And so now you know the data generating distribution, but substantially you're interested in how does each variable drive other variables in the system? That's encoded by the matrix M. If it's not identifiable, then you may know the data generating distribution, but there may be many ways in which it may have come about. So there may be many different causal ways of creating the same distribution. If it's identifiable, then you know only this parameter constellation could have given me that. Yes, the covariance matrix. I say, so in this problem here, I'm saying you give me a large data set for all practical purposes, I know the covariance matrix. Yeah. So then what exactly do I mean by identifiability? So there's two. Identifiable, that means that anytime you take a sparse covariance, a sparse matrix M, sparse over the given graph, anytime you take one and you compute the covariance matrix that it induces, then no other choice of M could have given that guy. Yeah, that's one option. The other option is that we call generically identifiable. That says the following. This says almost the same thing, except that there's these two words inserted. That means if I take randomly chosen coefficients and I fill them in the matrix M, then with probability 1, I will be in a situation where the covariance matrix I compute from that is such that no other matrix M that is sparse in the same way can give me that same covariance matrix. Yeah. Okay, so it's just whether it's for all or whether it's for almost all choices of M. And so just to give a, if you play around with this, so this is an example of a graph where I would have this global identifiability. This is an example of a graph where I have no kind of viability. I just added this edge here. If I add another edge, this would be an example of a graph where it's generically identified, okay? So this is can be a little delicate, right? Especially this notion. Okay, so then we first studied this global identifiability. And so this is where we got a nice result. So when you study this global identifiability, then you're back to one of college, right? So you're doing linear algebra. I'm asking you this. I give you a matrix sigma, and we know there is, and C we know, right? So we know there's some M sparse that solves this equation, right? And you have to determine whether it's the unique solution, right? So is this linear system, does it have enough linear independence in it? So this looks like a matrix equation, but if you want to, you can express everything in the customary format of a big matrix, and you take this matrix M and you stack its column into a vector if you want that. And then you have a linear system like you're used to it, a matrix, a vector, a vector. And the matrix that you have, you can express with some Kronecker product. So sigma Kronecker product identity plus identity Kronecker product sigma. And then this guy is the commutation matrix, which turns the row-wise vectorization of a matrix into a column-wise vectorization of a matrix. So this is an orthogonal matrix, permutation matrix that does this shuffling. So for example, if you're interested in a system with 3 variables, if you vectorize this Lyapunov equation, this is what this coefficient matrix looks like, okay? So it's a very sparse thing. You just pick out entries from sigma and distribute them in this sparse way. And so then the question is, what does this linear system do? And so this is what you need to do to check this identifiability. You give me a sigma, I have to check what is the solution space to this equation. If you know that this matrix M is sparse over the graph. So you only need to worry about those entries that correspond to edges in the graph, right? So you have a big equation system at first, which is here 6 by 9. And then you remember, okay, if I have 6 equations in 9 unknowns, there's a 3-dimensional solution space at least. Nothing you can do, right? It's not at it. But we know that it's a sparse situation. So we're only interested in some of these columns here, because only some of them will meet entries in M that are over edges of the graph, and that's then that. So at the end of the day, what you have to do is you have to take this equation system, you extract some columns from this first wide matrix, and then you get a system that has a chance of being square or maybe overdetermined, and then the question was whether it's a unique solution. Then you remember from your first math class that you have to look at the rank of some submatrices. And so the question is then, what is the rank of this matrix A sigma? Striking out some columns, leaving some columns intact. The number of which is the number of edges in the graph plus the diagonal entries the way I'm presenting this. And if for all matrices sigma that are realizable over the graph, this thing is of full rank, then there's always a unique solution to the linear system and you have global identifiability. And if you want to check in on generic identifiability, all you need to argue is that there exists one matrix for which the rank is full, then you immediately know it's almost always full. So this is the game of looking at the rank. So this is the kind of thing. So suppose this isn't one simple example. So this is a DAG in terms of if you don't think about the self loops, this is a DAG. This is the 6 by 9 matrix that is encoding the entire equation system if M is unrestricted. If you restrict to these 3 edges only, you strike out everything except for what's left here. And you see this 6 by 6 matrix. And then everybody can see that this always has full rank because this is sigma, which is positive definite. And this is a principal submatrix. And this is another principal submatrix. And this is block upper triangular. So this is obviously invertible. So a DAG here is globally identifiable, the parameterization. So you can do this same argument for any DAG, okay? So then I thought the answer is now DAGs are nice, cycles are bad. And then we did this example. So this is a 3-cycle. And then you look at the rank constraint and the determinant of the matrix you would like to have. The determinant of sigma factors out, it's positive definite, so that's positive, doesn't vanish. And then you have this difference. And over positive definite matrices, if you think about it for a moment, this difference is also positive. So it turns out that this cycle is also always globally identifiable, okay? All right, so then my easy conjecture was not true. So then we did more examples. So then, so I do what I can. So first did force, right? So then you have to do things like you get this polynomial and you have to explain why this polynomial is always positive over 4 by 4 positive definite matrices. That's not so easy. You can do some computational tools to help you realize that, but not so easy. And so then this was no way forward. But then after me giving enough trouble to Philip, we have a theorem, and that goes like this. So in the end, the story is this. This global identifiability we can characterize, and the answer is if your graph is simple, meaning that there are no loops of size 2, so no feedback between a pair of variables. Otherwise, it can be anything it wants to be. Then the model is identifiable. Then I'm in a situation that any parameters you assign are such that they uniquely define a covariance matrix. And I'm going to skip this, but this was the first time I had to do spectral theory for a non-symmetric matrix in I don't know how long, because I always do covariance matrix and they're symmetric. But so this was sort of fun. So you can bring in almost everything you learn about Jordan normal forms and eigenspaces and diagonalizability in this proof. So this is fun. So if you want to see it, I give you the slides later, or you look at the paper. But this is the theorem that we have. Okay, so it's not bad. So you get a lot of global identifiability, even with feedback cycles, just you can't have 2 loops to have that very strong notion of identifiability. Unfortunately, for generic identifiability, we don't have such good results yet. So stuff we need to work on. But there's also an interesting connection for people that know about treks. So the trek rule. So in the usual structural equation models, there's a result called the trek rule that tells you how you can read off the structure of covariances by looking at paths in the graph, okay? And in particular, if you have 2 nodes for which there is no trek in between them, so a trek is a path in which you first go up the mountain and then back down. So this is a picture of a trek. You go up and you go down. If they have a pair of nodes that are not joined by a trek, then in the usual graphical models, you know that there is 0 covariance between those 2 variances, that they're marginally independent. The same turns out to be true for these models, okay? Everything else you know about conditional independence in graphical models is false in these models, but that's yet to be proven too, that statement. But so this also says that there are some 0 constraints in the matrix. So you can use that, for instance, to give necessary conditions for identifiability. If you have too many variables that have no trek in between, you have a bunch of 0 constraints on the covariance matrix. That means you cannot have too many parameters in M to have hope for identifiability. But okay. Yep.
About this assumption in continuous time. It kind of seems wrong. It seems wrong, but in continuous time, your facts, certainly most of the time, they go. It starts at one time, and the effect is some biology arrives a bit like in continuous time. So maybe,
yeah.
Maybe at least for every case I can think of this whole stuff.
Yeah, I agree that it's sort of hard to think about sort of simultaneous things. In continuous time, things don't happen simultaneously. But yeah.
Good news for you.
Yeah, yes, well, maybe I'll quote you on that going forward. But yeah, I don't know, but if we study price and demand and I don't do it, like say we have a 2-variable system and I don't do the 2 loop, then it would have only flow one way, right? That would also somehow not be quite right? Is it? But yeah, I mean, I'm happy not to have 2 loops, yes. Okay, so this is what we know about identifiability so far, and so we're working on this some more, and yeah. So the other part is about estimation. So what I also found so fascinating is that we have this very obvious thing down a convex program, which, for instance, in time isn't that easy, because the discrete time analog of this question is not linear in the parameters, but quadratic, okay? So then it's not so easy to get a convex program. So this method was proposed under the name of direct lasso. So you look for an estimate of M that is such that you almost satisfy the Lyapunov equation while having small one norm, which is a stand-in for having a fairly sparse matrix. And so then the game is, then we said, now we're going to study this and say, how well does this do in terms of recovering the support of M? S is my symbol for the support of M if I need to have one S of M. And I guess M star are true drift matrices, M hats are estimates that come out of this program. So there's a picture I don't want to talk about. The method can do something, right? So it can detect some sort of signal in terms of area under ROC curves and so on. So you can, for instance, look at the paper of Niels and Gerardo Verando to see some signs of this doing something in terms of learning something about the sparsity pattern of M. So, but let me talk a bit about sort of how we try to theoretically analyze this. So when you look at it, it's, for instance, computation quadratic function with L1 penalty. It's a norm squared. It is literally a lasso problem in disguise. You just have to write it up in the right way. You stick it in your lasso solver. There's nothing to be done. So when I write it like this, you see that this A matrix that I displayed earlier, this gadget here, this one up there for the 3x3 variable case, inserting the sample covariances here. This is acts as the design matrix for the lasso problem. So the randomness is in the design. And this is given. So the response is a known thing. The randomness is in the design matrix. And so, yeah, written out, this is the Hessian, the Gram matrix. For this is then this A sigma transpose A sigma. And so computationally it's trivial. And it's also, there's an obvious way to analyze this by going through the textbook by whoever, Wainwright or so, and use this primal dual witness method that study to what extent is this successful in terms of learning the support of M. And so then you go through the textbook and you read along what you have to do. And so then what you have to do is you have to understand identifiability to be able to argue that the Hessian matrix over the signal submatrix is invertible. You take the usual assumptions known as irrepresentability condition, some signal strength condition. And then, okay, so to give a probabilistic guarantee, you want to say something like, okay, if I generate data from a distribution that is associated to the parameters or in some sparse matrix, then with high probability, my lasso method here infers the correct support back. In order to do that, you need to understand what happens to this Gram matrix. So this guy, A sigma transpose A sigma with sigma replaced by sample covariances. And you have to understand what happens to this matrix. How close is it to the true Hessian 2 Gram matrix in the columns that pertain to support signals you have to infer. And so this has to be, so in matrix infinity norm, you have to understand, can you control epsilon departures between estimate and true Hessian matrix for this problem? So the usual way people analyze this then in all these high dimensional statistics problems is to tackle this or to study this concentration in terms of entry by entry in this Hessian matrix and a union bound. Okay. So then we did that. And unfortunately, this gets extremely annoying because the entries in this matrix here are unfortunately static in covariances, and the number of terms grows with the dimension of the thing you study. So that means this concentrates very poorly entry-wise for some entries. So very poor concentration, and you get a very bad sample complexity out. So we're going to get another but slightly less bad sample complexity out by doing, so that's how we did it. We instead just said, okay, we're in such a realm where we might as well take a spectral perspective and just apply standard tools that say, even in spectral norm, at some point when the sample size is larger than the dimension, you're going to be able to control sample covariance matrix compared to truth in spectral norm and make high probability statements about errors there. And if our Gram matrix, it has these entries that have many terms, but it also has some nice features of being related to a bunch of Kronecker products. And so once you take a spectral perspective, the question is what happens to eigenvalues of this kind of thing? And if you have Kronecker products, eigenvalues are nice, right? So the eigenvalues of a Kronecker product are products of eigenvalues. And so this allows us to do with spectral norm things and just track errors in spectral norm and keep track of all these terms and get something out that's a little bit better. Okay, so at the end of the day, we have the theorem, like you're used to it for the last 15 years, that if you have a sample drawn from this setup with these Ornstein-Uhlenbeck processes in equilibrium with the Lyapunov equation giving covariance matrices, if there's a true stable drift matrix that has a support of size D, if the Hessian over the signals is invertible, there's an irrepresentability condition that holds, and so on and so on and so on, then we get out a sample complexity result that if the sample size exceeds the size of what you want to learn times the dimension, so this isn't really high dimensional in terms of sample size versus dimension, but on the other hand, we have p-squared parameters. But anyway, so we have a result like this, then things are good for some tuning parameter. You get the usual results. There's a unique solution to the program. It has support contained in the true support. It has a max norm estimation error bound that says if the signals are strong enough, you get the right solution. Okay? So this is just like it always is in the Lasso studies. But there's one more interesting thing, and that is the irrepresentability. Yeah.
I guess it's like a standard galaxy graphical models. Say,
yeah.
You talked about it. Do you think this is fundamental?
I don't know, but yeah. So why we have this result in this form? So in the usual graphical models, you have a Gram matrix that is block diagonal and very sparse. So when you do something like what is the maximum row sum, you don't sum over many terms. Our thing is dense with poorly concentrating entries and so on. So I don't really know what the real answer is, but so far I can only offer this. Yeah. I don't think it's evident that you should have something anyway like the graphical lasso or so. I don't think that's the case. But okay, so the other thing is irrepresentability, and this is even worse. Okay, so for the irrepresentability constant, you have to do something like this. So you take this Hessian matrix, extract the signal principal submatrix, and also the non-signal signal part, and you mingle it together by computing something like a regression coefficient from a covariance matrix, right? So this is like a formula for a regression coefficient. And then you have to essentially think about the size of this and get some gap to 1. And so we studied this, and so then I asked the question of, can you give me a single example where this works? Okay, I give you a graph, and you have nothing ambitious. We don't say that it is good or anything. I just want to know, is there even an example where this theorem applies? Yeah, and so not as easy of a question as you think, right? So so usually in graphical modeling, you do things like, if I take something close to the identity, things will work in terms of this irrepresentability. Here, if you take something close to the identity, or if you take something close to a diagonal matrix, so you take your signal M to be close to a diagonal matrix, the only way irrepresentability, the diagonal entries are ordered in the same way as the edges in your graph that you want to learn. So that means that if you want irrepresentability near a matrix that is close to independence of the variables, the only way you can get it is if the signals, they line up in according to the graphical structure that you want to learn, and this graphical structure is a DAG. Yeah? So I cannot actually currently give you a general recipe to construct an example that would say that this is not the theorem about the empty set when the graph is a cycle, okay? But I don't know. Well, okay, we can simulate, and I think there are examples, but I cannot construct you one in general. Okay, so if we do simulations, we do find one. They're not very common, but they do exist seemingly. But there's going to be a limit. So, and you sort of see this, right? So if I give myself a favorable situation where there's a path, a DAG, and I order the signals in a way that respects this DAG, I can get a method that with increasing sample size perfectly infers what. If I throw in another thing and I make this a cycle thing, then even for knowing perfect covariance matrix, you don't quite get it right. You make some mistake, okay? In that sense, I'm not sure that there's often a gap to what you really can get. So you learn something, right? You learn a lot of edge structure correctly, but perfectly right is not a given here. So now, instead of lasso, we're doing some mixed integer programming. We're encoding, instead of an L1 penalty, just looking at L0 and counting the entries in M and maybe putting a bound on that and then seeing how well can you satisfy the Lyapunov equation. And so with these kind of methods, so I don't know, if you've seen this, people talk about these using mixed integer programming for best subset selection in regression. So we're doing something very similar, just like earlier it was this direct lasso was just an instance of a lasso problem computationally. We can do the same thing here. And then we can manage to, maybe I'll stop in with this one. So you can actually then outdo this direct lasso in terms of doing better than it. And I think this is then due to this irrepresentability, which sort of limits you or prevents you from getting a perfect recovery. So, but this we haven't written up. So this is just a bunch of random plots. But so this plot is supposed to show you that with this best subset selection, you can outdo the lasso. And I think this is due to this irrepresentability issue that prevents you from being perfectly consistent here. Okay. So then I'm going to stop. So this is what we know so far. So this global ID question we could solve. We know about, there's this track rule that says something about when are things uncorrelated in this system. I have a conjecture that there is never any non-trivial conditional independence, but there we have some things to finish. This direct lasso, which I think it's useful. It gives you something not unreasonable, but it's rarely consistent, I would say, and because of irrepresentability. Doing this best subset selection stuff is computationally more expensive, but I think if it's feasible, this is something interesting to do. And then other things we work on now is, I didn't bring any slides for that, but this assumption that C is isotropic is, of course, also strong. So a natural other scenario to study is whether this matrix C that describes it's in some way the variance of this noise that comes in. Where's this? Yeah, this matrix C, right, is related to this noise here. Another reasonable assumption to say is that this is an unknown diagonal matrix, not a multiple of the identity, but an unknown diagonal matrix. And so then all these questions start anew. And so you can think about a version of this lasso problem and the identifiability question, but there, yeah, we're not that far yet. So but anyway, so lots of things to look at. And this is what I meant with this dot. So there's lots of things you can think about. You can also do non-Gaussian processes, another thing we've been looking at. So instead of having a Gaussian process driving as a noise, you can do some sort of Levy processes, and then you can look at higher moments, not just covariances, but third order moments and higher order cumulants. And that gives you a lot more information that you can maybe work with to say something about identifiability or estimating the drift matrix M. to be done. But so there's a lot to be done here. Okay, thanks.
Please raise your hand. If you're on Zoom, you can also raise your hand.
Yeah, so having C not diagonal is interesting to model scenarios where you might have this as a bigger system involving additional variables that you have then actually observed. So you can play this game so in structural equations, you can play this game of saying that I'm thinking about some scenarios where there's some variables in my system that ultimately remain latent, unobserved. Then you can, for some purposes, it's interesting to then just compactify the representation of the model and say, I'm going to absorb the effect variables into an error correlation. And so you can do the same thing here. So you can say, I start with some 20-dimensional process, but then ultimately I only observe 15 dimensions. And then I have 5 other things. And if those act sparsely, then you can describe how you would need to structure this matrix C non-diagonally, but maybe still sparse, to capture, to make sure that the marginal of the big element of the model you associated to this C non-diagonal. Does that make sense? Yeah, so you can as well. So you could study also identifiability in this setting, but it is, maybe also I didn't say this very explicitly, but if you want to hope to identify something here, you have to have a large sparse system. So if you have only 2-3 variables, there's effectively nothing you can learn. Right? Most things are indistinguishable and so on. So you have to have a system of a bigger size and sparsity to be able to learn from just the covariance matrix structure here. So if you look at third moments and so on in non-Gaussian settings, this may be different again, but at least learning from just the covariance matrix of a cross section is sort of ambitious, right?
There's no more.
You know, you talked about the global identifiers. Where did this the amount of sparsity come in?
Okay, so if you're not sparse enough, then it's clear you can't do anything, right? Because you have, if you have no sparsity, then you're in this situation. So here. So if you have no sparsity, let's say you have a 3-variable system, then you have a matrix M with 9 entries. And the Lyapunov equation involves symmetric expressions, right? So this, if you transpose this, it's the same. And the C is, so this is a symmetric matrix equation. So effectively, this gives you 6 equations about 9 unknowns. So you have to have some sparsity to get going, right? So at most in this 3-variable setting, if you want some identifiable situation, you can at most draw 3 edges into your graph because you already have the 3 diagonal entries in M, these self loops. And so, and then the question is, well, how exactly does this sparsity need to be structured to get identifiability? And yeah, and so then if you don't have 2 cycles, you're always okay. And I don't know. If you, so the proof plane, the crucial thing is, because I don't have 2 cycles, if I take the square of the matrix M, its diagonal entries are the squared diagonal entries of M. That's sort of a very important for this 2-cycle thing mathematically. So, but that is not very helpful. Is that a reasonable answer or?
Yeah.
Yeah. Okay.
No.
Yeah. Okay.